All right. Thank you for your participation. Had to pull teeth to get it. So we just discussed that this has 2 degrees of unsaturation. How did we find that out? To chicken rule. We plugged it in and said there's 2 degrees of unsaturation, and we decided that there are either 2 pi bonds, 1 pi bond, 1 ring, or 2 rings. Of those combinations of degrees of unsaturation, which is not shown on the board? 2 rings. And I might be wrong, but I think there's only one way to do this. There might be 2 ways to get 2 rings. Here's one of the ways. 1, 2, 3. Oh, no, that's not it, because that's not 4 carbons. All right, so there's 1 ring, or bicyclic ring, I should say. And I have this little CH3 group coming off, but I could have put that on either one of these positions. That'd be a structural isomer. You guys agree that's 2 rings, right? There's a 3-membered ring on the left and a 3-membered ring on the right. It's kind of a weird 3 rings, but it is. But because I had actually 1 extra carbon, I could have done this as well, a 4-membered ring on the left, a 3-membered ring on the right. I could have made my nitrogen a part of the 2-membered ring and had a 3-membered ring on the right. And then, of course, I could have my nitrogen sitting at the vertex of these 2 rings. That's another structural isomer. And then there's a way that I could have a ring where 2 rings are coming off from a central point. So that's 1, 2, 3, 4. That's another bicyclic structure that I could have. And I think that's all of them. All of the 2 ring versions. Some of you guys have repeats up here. For instance, this one, where there's a triple bond to nitrogen at the end of the chain, is the same as this one, where there's a triple bond to nitrogen at the end of the chain. What's the difference between them? Their orientation in space, but their structure is identical. You just have to flip it around 180. There's another 2 that are the same. I think I noticed. This one here is the same as this one down here, where the nitrogen is in a 5-membered ring and has a double bond. What's the only difference? Again, it's been flipped upside down, flipped like a burger. That's the relationship between them. These 2 are very similar but distinct structural isomers because of the placement of the NH2 group. What's an NH2 functional group called? Amine, specifically a primary amine. So the relationship of the primary amine to this changes. Here it's an amine. Here it's an enamine because it's attached to an alkene. Here is another enamine where the double bonds are on the carbons. I could get a similar structural isomer to this, where I actually have both of the double bonds center at 1 carbon. We call that not just a dialkene, but a cumulated diene, because the 2 alkenes meet at the same carbon. And we're not breaking any rules because there's not 5 bonds going to it. So what I want you to recognize is that with such a small chemical formula, there is almost an endless way to draw these structures. And yet, throughout the semester, there is very often one correct answer based on the way the structure is given to you and the product that you're needed to predict at the end. Does that make sense? Be creative, come up with as much as you can, try to find that one right answer for reactions that we study, okay? Any questions that you guys have on this? Oh, Will, I did kind of, I threw you off with this one. This has How many degrees of unsaturation? 2 pi bonds, 1 ring. So that's got 3 degrees of unsaturation. Which pi bond do you want to get rid of? That would solve the molecule correctly. How about we just get rid of this one? And now it's solved.
Oh, I see it. Yeah. I see. Yep.
What did I just change about the chemical formula by getting rid of that pi bond? I added in hydrogens. How many? Yeah. There was 1 hydrogen here, 0 hydrogens here. Now there are 2 hydrogens here, 1 hydrogen's there. Does that feel easy for you to recognize yet? Then you've got to practice. Keep practicing. And if it helps, sketch them in any chance you can to remind yourself that they're there. You just need to watch out for 5 bonds. Don't convince yourself that there's a hydrogen here just because you assume there must be one, because there is no hydrogen there. Cool. All right. Well, I would love to draw all of them, but I just think it would bore you guys. So I think we'll move on. How does that sound? We're going to spend today, because I always try to cram it into less than a day, and I think this time we're going to spend the day on it. We're going to spend the day on nomenclature. You guys have learned about nomenclature in general chemistry, but it's very likely you've forgotten what it means. Can anybody remember? Nomenclature? Yeah, I think it's Latin for naming convention. So it's our system of naming. And we're going to be using IUPAC nomenclature. You guys, have I talked about IUPAC? Do you know what IUPAC means? International Union of Pure and Applied Chemistry, which to me sounds like such a highty-tighty name, you know, pure and applied chemistry. I would say a lot of people hate IUPAC. I don't mind IUPAC. It has rules which makes molecules systematic in their naming, so that you don't have to guess at how to name a molecule. You can just follow the rules and you'll have its name. Most IUPAC names can be broken down into this format. There's some prefix followed by a root, a locant, and a suffix. We're going to dive into these 4 parts. Although, a quick spoiler alert, the prefix often contains at least one piece that has a locant, a root, and a suffix of its own. At least one piece, sometimes multiple pieces, each with their own locant, root, and suffix. Notice how I've placed locant relative to root and suffix in black compared to how I put it in green. We're going to use locant to describe something different in the true compound's root or suffix versus inside of the prefix. It's going to kind of be oriented differently. All right? First, let's start by talking about root. The root describes the number of carbons in the parent chain. Why use parent when I can use another word? What is the other word I could use? Primary, I would agree, I'd give it to you, but it's not descriptive enough yet. Or I think I'd say it's as descriptive as parent, not as descriptive as another word we could use. What is the parent chain? It's the longest parent chain, or the longest carbon chain. So what breaks up a carbon chain? Heteroatoms, or rings. If you have a heteroatom bonding two carbons together, that's two separate carbon chains. If you have carbons in a ring that are bonded to carbons in a straight line, those are two separate chains. They are not continuous. So rings and heteroatoms break up our longest chains. I think you guys will be familiar with some of these prefixes, others maybe not. Let's look at the first four prefix terms that we use for root. If the longest carbon chain is 1 carbon long, we give it the root meth. By the way, we're gonna reuse these roots when we talk about roots in our prefixes. We're just gonna change what the suffix is. So a 1 carbon chain that's in the prefix rather than in the parent chain still gets a meth root. 2 carbons, F. 3 carbons, prop. 4 carbons, bute. I feel confident that you all could name an organic molecule that starts with each of those 4 root terms. Somebody give me meth. That sounded really weird. Don't take that out of context. Methanol. Great. How about another one? A little bit more universal to us all. Methane, aka natural gas. So if you have ever been in a building, probably this one, heated by natural gas, you've been impacted by methane. Okay, good. Methanol is another great one. Elise, did you give me that one? What do you use methanol for? Why do you know methanol? Okay, good. I want to say some people that work in labs use methanol sometimes as a cleaning thing, but more people use a chemical that starts with F for that. Ethanol. You might also poison yourself if you intake ethanol through liquor or any alcohol beverage. Not all alcohols are the alcohol you drink. Please don't drink methanol. You want to hear a sad story? There was a college party, I think in Arizona, where it was a bunch of underage kids, and one of them must have worked in a lab, got their hands on methanol, thinking alcohol is alcohol, let's have a party, and they spiked the punch with methanol, and they all died. And they all died at the party. They had alcohol poisoning. If you ever ingest methanol, your body metabolizes it first into formaldehyde and then into formic acid, both of which are pretty toxic to your body. The only way to save yourself from methanol poisoning is to outcompete the metabolic process with ethanol. You have to drink to save your life. It's really strange. They did it on an episode of House, and it's real. They did. Guy came in with methanol poisoning. They just had him drink vodka because all that ethanol is now out-competing the metabolic process of methanol, and his body can just flush out the methanol. Crazy. It's actually a little bit similar to if you get carbon monoxide poisoning. Carbon monoxide binds to your hemoglobin so that oxygen can't bind to it. So in order to get rid of carbon monoxide poisoning, what do? You go in a hypobaric chamber where you get flooded with oxygen so you can try to outcompete the carbon monoxide with extra oxygen. Except oxygen's not bad for you. Prop, a compound that you all know of that starts with prop. Propane, fuel. And bute, butane, another fuel. Those are the 4 oddest root terms. They don't really come into play outside of organic chemistry. I'm not interested in you knowing beyond 9 for this class. But beyond 9 is not hard. You just have to be familiar with how to combine Latin prefixes. Like 10 is dec, 11 is, I always forget, undec, 12 is dodec, I think. Yes. Like a dodecahedron is a 12-sided die. So in this class, we're not going to name anything past 9. It's not that much harder. It's just a lot less common. 5, the prefix we give is pent, and then hex, and then hept, oct, and non. I would say the only two that I've ever seen students confuse are 6 and 7. What do you think students confuse them with? Hex is great. Hexagon is a 6-sided thing. Instead of hex, I've seen students use what? What's the only other term you've heard for describing 6 things? Half dozen. Half dozenane. It's not hexane, it's half dozenane. Imagine you have twins, a triplet. What happens if you have 6 kids at the same time? They're not hextuplets, right? They're sextuplets. And if you have 7, septuplets. So I think these are actually Greek. I think I misspoke earlier when I said Latin. These are Greek. Sept and sex are Latin, I think. It doesn't matter because you just have to use them. Who cares what language they came from? Just don't get them confused with that. In my opinion, hex and hept make more sense because they come from the same ones we use in math a lot more commonly. Okay, that's it. If your longest carbon chain is that number long, that's the root of the compound. Unless you have a cyclic structure. You just add cyclo with the root, and that is the root. The root becomes cycloprop, cyclobute. Are there any cycloprop root compounds on this side of the board right now? Yeah. Right here is a 3-membered ring, cycloprop. Here's another, here's another, here's another. 3-membered rings. Are there any cyclobute based rings anywhere on this board? Just right here. That's the only cyclobute on the board. Are there any cyclopent based compounds on the board? Oh yeah, you're right. Those are also cyclobute. Thank you for pointing those out. And that one up there. Cyclopent. Are you counting 5 carbons or are you counting 5 atoms? These that have the nitrogens in them are not 5 carbon chains. They're 5 atoms, but they're not cyclopent because it doesn't describe the number of carbons in the chain.
I don't think we could have a cyclopent because we only have 4 carbons.
Good point.
So it's a cyclic structure if the longest chain is the ring? Is that how we define a cyclic?
Yeah. Well, I mean, any compound that has
10, is that still a cyclic structure?
Wait, what?
It's like a ring and then a tail of like 10 carbons. Is that still a cyclic
Sure.
structure?
Yeah.
So you would still name, but there's...
Well, the thing is, whether the ring becomes the parent or not the parent depends on where is the longest carbon chain. If you have a 6-carbon chain, a 6-carbon ring, and a 2-carbon chain coming off, 6 carbons wins. But if you have a 6-carbon chain and a 3-carbon ring coming off, 6 carbons wins. And that's actually what we're going to say next. Parent chain goes to a chain or a ring, whichever is longest, never both. And I'm putting both in quotation marks because anybody that is familiar with organic structures is going to say you can't have both. But I see so many students being introduced to organic chemistry that say, just do both. By the way, I'm not necessarily against showing you 7, 8, and 9-membered rings, but they are more challenging to draw, and we're not going to draw them often, so it doesn't really feel worth it to go through it. We are going to draw these other chains a lot more often. So maybe if you want to know what these look like, it's triangle, square, pentagon, hexagon. Not hard. And actually a 7-membered ring is not hard either. You just have to like plan for it. You have to know where your angles are going. It's actually the octagon that is the hardest for me. Because at least there I can count all of them. But when I do my octagons, it's like the angles are just so big I can't figure it out anymore. And I'm sorry, I didn't plan to do this, but actually the 9-membered ring is a lot easier than you'd think. Wait, I don't think that's it. It is if you take a hexagon and then combine it with a pentagon and cut out the middle, you get 9 members. 6 from this, and then an additional 3. And a 10-membered ring is just 2 hexagons sat next to each other with the middle gone. It actually gets easier after 8, but harder. 7 and 8 are the hardest.
Do they not like forming like big long rings past a certain point?
No, you can get pretty big rings. Macro cycles are possible, like 20 to 30 member rings going around. But they are definitely more of a challenge to synthesize and purify. So take this compound, which is a hexagon with a 2-carbon chain coming off. Here is what I've seen students do. To try and figure out the name of this compound, they will count all of the carbons. They'll start here and say 1, 2, 3, 4, 5, 6, 7, 8. And they'll say that this is cyclooctane. No, it's not. It's not an 8-membered ring. And it's not octane either because it does have a ring. So when you have a ring and you're trying to determine the longest chain, find the carbon that is outside of the ring and the carbon that is inside of the ring. They cannot be counted as part of the same chain. If a carbon is in a ring, it must be counted as in the ring. If a carbon is out of a ring, it cannot be counted in the ring. What is the root that you would give to this parent chain? What is the root for the parent chain in this compound? What is it? What's the root of the parent chain? Cyclohex? As opposed to F. F would be the parent chain of this, but it's not the longest carbon chain. It's only 2 carbons long. Okay, let's do another one. what is the root for the parent chain in this compound? I don't think so. Oh, yeah. That's not what I thought I put. I've got prop on one side, bute on the other, so the root for this compound is bute. All of the other carbons that you see, all of the other atoms, they're going to show up either in the suffix or in the prefix. But for now, we're just focusing on this longest carbon chain. Not just pent. Cyclopent. Because it's that ring. That functional group. Can you name it? It's a carbonyl, which is, carbonyl is not a functional group. Carbonyl is a family of functional groups. All you've done is recognize that a CO double bond is a carbonyl, but you haven't told me which one. This is a ketone. It's distinct because on either sides of the carbonyl are carbon atoms. Why is it that the ether in this compound decided that you split between 3 and 4, you don't count them all as 7, but here the ketone doesn't split it. You don't have to minimize the parent chain at all. Why does the functional group split the parent chain here but not here? Do you see what I'm getting at least? Yes. The carbon chain is unbroken, despite having different bonding in certain sections, whereas here, the carbon chain is broken. Okay. Here's a fun one. I put this as a bonus problem. Oh, no, sorry, that's not. We'll have to get back to that later. I can't give it to you yet. Okay, let's do another one though. F. Either side, right? This is only 2 carbons long. This is only 2 carbons long. I actually can't count all 3 of these carbons here. Oh, actually, no, I could actually. Sorry. We can. It's because I was thinking of naming this a different way. But 1, 2, 3. So we could call it what instead? Probe. Aha, tricked you so good, I tricked myself. All right, now here is a more challenging one. What is the longest carbon chain? What is the root for this compound? You said what? You guys agree? How did you get there? Where'd you start? On the right or the left?
I started from the right, but it was closer, and then I think you can start from either bottom or the rightmost one, and then just ignore the one dangling off, and then
Go up.
yeah.
Good. Kind of a weird route, right? These structures don't have to be read left to right. They can be read top to right. 1, 2, 3, 4, 5, 6, 7. Happed. Clear enough? Ready to move on from root?
So anytime there's a, I guess like the terminal
now the one above that is confusing me. 'Cause
Here.
yeah. Because if you're going, so isn't that? Oh, but you're still okay. Never mind.
Yeah. So you could call this compound 2N-ethylamine. Sorry, 2N-ethylaminopropane, where this is the longest carbon chain. Off of the second carbon is coming in ethyl amino group. So yeah, the longest chain could be read that way. The reason I said F originally and agreed with Hayden was because I was naming it via a different naming convention, which is functional class. So I was going to name it isopropyl or ethyl isopropyl amine, which can also be called methyl ethyl. And so I was throwing myself off. It was not what I wanted to get out of that. Okay, but we recovered and we move on. Root is typically pretty straightforward. There are instances where the longest carbon chain actually gets deviated. So one caveat that we will come back to add here is that we're looking for the longest carbon chain with the highest priority functional group. So how do you decide the priority of the functional groups? It's given to you. IUPAC has already decided what they would be. I'm not going to have you memorize all of them. For this semester, you only need to know the priority of alkane, alkene, alkyne, alcohol. However, it can be useful to know beyond that. So I'm going to show you a resource that you can use if you want to go beyond that. If you are going into OCHEM 2, then it's almost for sure that you will need to know beyond just alcohols. And this resource, it's good. I will say this, IUPAC is not clear about why they chose the order they chose. And I have a big grievance with that. I would like to know what it is so that I can explain it to you. I can only offer a justification at this point. So if you come to the online textbook that I've linked on your homepage, this is an external resource, not a part of our course, but it is useful. And if you scroll all the way down to Appendix A, Nomenclature of Polyfunctional Organic Compounds. First, it gives you all of the functional groups in alphabetical order of where they show up. I don't want to do that. Then it gives you this table, their classification, and they are ranked. You know what, I'm just realizing I did a nomenclature exercise last night with OCHEM 2, and I told a student he was wrong, but actually he did do it right, so I have to apologize to him. They're already ranked by order of priority. So carboxylic acid is the highest priority functional group. If a compound has a carboxylic acid in it, you look for that carbon chain as the parent chain. Doesn't matter how long or how short, that's the parent chain. For example, let's say that I've got this aromatic ring. Doesn't even need to be an aromatic ring, don't need to throw you off. I've got this cyclohexane ring, and over here, I've got a 1 carbon chain with the carboxylic acid, and over here, I have a, I don't even know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon chain. 10 does not win as the parent because the carboxylic acid is the highest priority functional group. How long is that carboxylic acid's carbon chain? Just the one carbon. And then it's the carbons of the ring, and then that 10 carbon chain. And those are not the parent of the molecule. Strange, right?
Is it because it affects the chemistry?
Nope. It's just a systematic way that we've agreed to name them. Or maybe not so much agreed, but are forced to. So, carboxylic acids are at the top of our list. I'm going to abbreviate that as CA. I'm going to skip a few and show you some others that I like. For instance, esters also get to the top of the list. Esters are very common functional groups. Acid halides, amides, nitriles get up here. We're actually going to name some nitrile. No, we might not name nitriles this semester. You'll name nitriles in OCHEM too, but we will see nitrile functional groups this semester. We just won't name them. Nitriles are also called what as a functional group? Do you know from your sheet? The nitrile is, oh, actually it tells you right here. They're also called cyano groups because the nitrile is that CN triple bond that a lot of you were drawing up here, which looks like cyanide attached to a molecule. Then we get aldehydes after we skip a few. And ketones. Aldehydes and ketones actually share priority. Neither one is higher priority. However, if both are present, priority goes to the aldehyde. And that feels weird, but we're going to talk about locant, meaning a descriptive location on the carbon chain. And aldehydes, remember, hide at the end of a carbon chain. They're always carbon 1. So you'll always get a lower locant set if you start with the aldehyde, so you prioritize it over the ketone. Then, as we come down, you'll see that the next one is alcohols. We're going to be starting here this semester. This would be our highest priority functional group this semester. As you come down from alcohols, we're going to name alkenes and alkynes, which are also tied. These have the same priority as each other, but if they are both present, you actually prioritize them by whoever can get the first locant, the smallest locant. And if there's a molecule where they both have the same locant, you prioritize them alphabetically. These are the rules of IUPAC. Typically, go for small numbers. If that can't win, go alphabetically. Small numbers, then alphabetically. And our last priority group, it's a bit confusing because it says alkanes are up here, and then it says subordinate groups, which feels rude. I don't think they needed to say that. But alkanes and halogens, alkyl halides, those are actually going to be tied. I'm not going to put halides, I'm going to put halos, because we're going to be calling them fluoro, chloro, bromo, iodo. They're tied with each other. You do not prioritize one over the other. That's our priority list. And just to keep in mind, we're going to be dealing this semester with alcohols, alkenes and alkynes, alkanes and halogens. Deal? But these are some other very common groups that you're going to see, and I think it's important to know how they play a role in naming now. So I want to deviate a little bit. And give you guys this structure. What is the longest carbon chain that contains the highest priority functional group? What functional groups do you see? Sorry? No ketone. No oxygen. Alkene. Carbon-carbon double bond. What's the longest carbon chain that includes the alkene? I can either go 1, 2, 3, 4, or 1, 2, 3, 4, 5, 6. 6. Despite the fact that I could go straight across and have 1, 2, 3, 4, 5, 6, 7. There is a 7-member chain, but it doesn't include the alkene. So I have to go with this. Hex is my root. Okay, now this was a bonus problem that I put on last year's final. What is the root for the parent chain of this compound? The longest carbon chain that contains the highest priority functional group. Why don't you think about it for about 10 seconds? Reason through the rules we've talked about. Turn to your neighbors and see if you agree on the longest carbon chain that contains the highest priority functional group. What are your options for the root? There's only 2 options. Cyclohex or F. Correct? What functional group is in this molecule? Alcohol, which has higher priority than alkane. How long is the carbon chain that the alcohol is on? Just 2 carbons long. So over here we said the root is cyclohex because there was only alkane. And here we're saying that the root is F because we're prioritizing the carbon chain of the alcohol. Does that make sense? So naming that was one of the bonus questions last semester because I thought it was fun. Flips it on its head, right? Okay. After looking at root, I want to take us to look at suffix. The suffix describes the highest priority functional group. Actually, I put it in parentheses. Highest priority functional groups. Because sometimes the suffix can describe more than one functional group. Now, rigorously, I like to say that there is a difference between a suffix and a suffix stopper because some functional groups do not go directly after root. They need part of another suffix. So suffixes come from your hydrocarbon chains. alkane, alkene, and alkyne. I think you guys know, if it's an alkane, the suffix becomes, maybe you don't know, methane, propane, butane. The suffix becomes ane. If it's an alkene, the suffix becomes ene. If it's an alkyne, the suffix becomes ine. However, if a compound contains both an alkene and an alkyne, then the suffix describes both. The suffix becomes ene, ine. Notice how you'll never have ane, ine, or ane, ine. The ane either gets dropped completely or it's the highest priority functional group. But the ene and the ine, they're only ever described by being in the suffix. So if they're both present, they both have to go there. I also want you to notice that the alkene actually dropped its E in order to make space for the ine. This is almost an example of suffix stoppering. I took the suffix "ene" and I stoppered it. I added another little suffix to it that was "ine." And that's what our other groups do. So in order of these groups, the suffix stoppers for carboxylic acids, we get oic acid. For example, I can have a suffix anoic acid. Oops, why did I put a B? Like methanoic acid, ethanoic acid, propanoic acid. I have a suffix of ane from alkane, and I stopper that with oic acid. I can also have enoic acid and inoic acid. If I have an ester, the stopper is O8. So I can have something like enoate. If I have methyl 2-butenoate, I have an alkene in my functional group, or in my carbon chain, and I have an ester. I get the ene suffix, and I stopper it with O8. You guys see where it's coming from? If I have an aldehyde, the suffix becomes al, and so I can get something like ine-al if I have 3-pentyne-al. My compound has both an alkyne and an aldehyde. A ketone, actually I do want to point out something. You see where the aldehyde suffix stopper comes from? Comes from al, aldehyde. What do you think ketone gets? But it would suck to name compounds with "-ete", right? And especially to put like an N with a K following it. So instead we end it with "-one", like testosterone. That has a ketone functional group in it. So here's an example. We could have ene, ine, "-one". Now it sounds like Old MacDonald had a farm. And this is really just to give you context, but you're not going to have to use these this semester. But I think that if you would go and look at your compound or other compounds you're interested, you'll often find suffixes like these, indicating you've got some functional group in there. The one that you'll need to know well this semester is alcohol, which ends with "-all", not to be confused with "al", from the aldehyde. This is the OL. And so here are the versions you can have. You can have an all, een all, ein all, and een ein all. Methanol, ethanol. You've got the suffix ein, and then the suffix stopper all. And I should point out, I know I gave you these priority of functional groups. Alkyl halides or halo groups, these are always in the prefix. I don't know, I should keep it consistent, right? So the halos, those halogen groups, they never show up in the suffix. All right, I want to give you guys a quick break to move around and get your blood flowing. I'm going to pull up some examples where we can apply what suffix would be present in a compound based on the functional groups that we see, okay? So take 5, get up, move around, and we'll come back in here. Bye, Belen. Have a good night. Hello. I don't think that I graded her unit test, so I think that she did. This is the hardest part for me, is I just get used to people not coming for attendance, and if they don't message me to tell me, yeah. Mm. Oh, I did. I still have her. on here. Different amount for both. Yeah. And they don't have to be the same sheet of paper for the final. Yeah. Like 2 front sides is great. October 22nd, or the Wednesday of that week, anyways. The week after fall break. If that means anything to you. Okay. All right, guys, I forgot that I had this activity. So this goes back to root. I just uploaded this activity. Here's a fun fact. Last summer, I interviewed to become a tenure track professor here after teaching here for like 3 years, just basically as an adjunct. And my teaching demo was on nomenclature. I had to teach organic nomenclature in 25 minutes. I was supposed to give a 25-minute version or like an example of what I would do in 25 minutes. And instead, I tried to fit the whole thing into 25 minutes, which is silly. I would have done it like I'm doing it now. I would have introduced the way the names are broken down, and I would have spent the first 20 minutes on just learning about roots, right? But I didn't. Well, clearly it didn't cost me my job, but this is an activity you guys can go back to throughout the semester. I just uploaded it under our top module, course resources, IUPAC activity. And the whole point of it was, this compound is sorbitol. How many of you have heard of sorbitol? It's a sugar, right? And then Freon, 112. And the point was, how do those names communicate anything about the compounds? And this is the value of IUPAC nomenclature. There's a systematic naming that gives you all the information you need. So this was the root practice, figuring out what root goes to each of them. I think that we had a fairly similar experience, maybe a better one with the examples we did. But you can see you're just finding the longest chain. And then I think it's the same structures. And now the question is, what is the suffix that they would all get? So can someone give me the suffix of the top left structure? Use what we talked about. This one here? No. Because an E-N-E, ene, requires an alkene. What is the bonding pattern of an alkene? Carbon-carbon double bonds. No double bonds. The only thing here is carbon-carbon single bonds, so we get ane. What suffix would go here? Let's take a step back on this one because I think it'd be worth it. What's the root of this compound? No. Alcohol is the highest priority functional group. What carbon chain is it on? A ring. How big is that ring? 6. So cyclohex is the root for this one.
So I was going to say, if the alcohol is part of the ring,
That's right.
you count the whole.
The whole ring. Yep. Just like in our other example, which was the cyclohexane with the 2 carbon chain, we didn't call this meth it's a part of a 2-carbon chain. We called it F, right? Part of a 6-carbon ring, cyclohex. What suffix would you get? Remember that alcohol stoppers a suffix with all. So you have to both pick a hydrocarbon suffix and an alcohol suffix stopper. What do you get? You want to spell it? Yes. Alkane, all. Good. Okay, what about the next one? Hydrocarbon suffix and functional group suffix stopper. What is the suffix you would choose? Ein, or ein? Ein, because there is a carbon-carbon double bond in that structure. What is the suffix stopper you would choose? Nothing or something? Own, for the ketone that's in there. It's a carbonyl with a carbon on either side. So put it together. Enone. Good. All right, I'm going to divvy up the rest of them. So Kiara and Will, I guess you guys are kind of on better sides. Andy and Will you guys do this one? Jackie and Kiara, give me this one. Hayden and Elliot, this one. Aiden and Elise, give me this one, the suffix. I think I'll have Nicole and Natalie and Alyssa all do this one together. Kiara, I'm going to come back to you, and we're going to go on this one. Peter and Indigo, back up to that one. And Sarah and Dee, back down to that one. Come up with the suffix that you would give it based on the highest priority functional group. If you figure yours out, go to another one. Try to find the hardest. So first, look at the structure and try to describe it. It would be from there. Can you describe what is wrong with either side? What alkenes and alkynes are good? What's wrong with both? Good. Yes. Now, according to our list, it's suffix is on alkyne. Good. Good. But that's a suffix stopper. So, does the rest of the structure have alkane?
There's only carbon-carbon single bonds in the alkane.
Oh,
There's carbon-carbon double bonds. There's
yeah.
if there's that thing that's double bonds, and if there's one bond, alkane does not have one.
I think that he was saying is that you drop
It's not carbon-carbon double bonds. But actually, these two are higher priority than this. So if either of these are changed, their suffixes go up. But if neither of these are present and then they aren't, then we have to change. So how do you know how to use alkane?
I think it's very
If the suffix
no, there's no function groups, and I'm always
other way around.
Oh,
So it's right there. Yeah. Don't think too much about it. Yeah. Not quite far less. So it's that's where the alkane is. It's not a carbon-carbon double bond. It's a carbon-oxygen double bond of an alkene.
yeah, Jesus is not
Yeah. Or not alkene. Which one is it? Like, just like yep. So there's nothing, there's no none of these are primary functional groups on our list up here. Right? This is an ether, a nitrile, a halo. They're not going to change the suffix. So then do we have alkane, alkene, or alkyne? No alkene, there's no carbon-carbon double bonds. There's no carbon-carbon triple bonds. But there are carbon-carbon single bonds. Alkane, so the suffix is just ane. Exactly. All right, can we go through them? Will and Andy, what did you find for your suffix here?
So there wasn't. We noticed there wasn't any other than obviously these three. There weren't any like other heteroatoms. So there was only we were only really working with these three.
Okay.
And there's a triple bond, which told us that it was an ine.
Good.
Yeah.
That's it. Your suffix is ine, no stopper. And despite most of the molecule being alkane, it's not ane-ine. Ine overrules ane, takes the suffix, right? Good. Jackie and Kiara, I think you guys had this. What'd you come up with? Sarah and Dee, you guys also had this. What'd you come up with? Ane. The ether, the nitrile, the halogen group, they're not going to change the suffix at all. So the only thing you have is carbon-carbon single bonds in the ring. So the suffix is ane. Let's see. Hayden and Elliot, what suffix did you give this?
Well, as the ketone as priority of the alcohol, we didn't know if you needed to include both.
Oh. Does this compound have a ketone? Does this compound have an alcohol? This compound does not have a ketone or an alcohol. That's right. This is one functional group, and it is, nope. What is this functional group? Carboxylic acid. I'm glad you said that because this is a very common pitfall. I see it. Look at it. It's a carbonyl group and an alcohol, right? But it's not an alcohol. Because it's part of that carbonyl group, It's all the carboxylic acid. So it's going to get stoppered by oic acid. Are you going to prefix it by an, ene, or ein? Yeah. Anoic acid. Good. Aiden and Elise, what'd you come up with here? Do you guys do this one too? What'd you come up with? Ain? Because that halogen group doesn't change the suffix. Good. Peter and Indigo, did you come up with the same? Okay, sorry, I forgot to come over to you. And Kira and I worked on this one. What hydrocarbon suffix does this get? Just alkane, because there's no carbon-carbon double bonds. Despite there being a double bond to a carbon, it's not a carbon-carbon double bond. And then it gets stoppered by al for aldehyde, because this is your aldehyde functional group. So this is anal. Say it right.
Okay, so on
I told you I'd get some good chuckles, didn't I? I did.
ours, if it did have a ketone and an alcohol, would you only include one of those in the suffix,
Yes.
the higher priority one?
Yes. Actually, this is a good point. We won't have to deal with it because we're only dealing with the alcohol as a suffix stopper. But when you have multiple compounds that both, or multiple functional groups that both stopper a suffix, the highest priority gets to stopper. The other functional group has to be named as a prefix. Can't be named in the bottom. So for instance, you can't have an own all, because you can't have all of those suffix stoppers together. Good question. You won't have to deal with it here.
So you're only ever going to have a stopper and then one of that A and E or I.
And I would say it in the other direction. You're going to have the hydrocarbon suffix and one stopper. That's it. Good. But there is an issue that arises if you have multiple of these groups. And that's where you get multipliers. So you can have something like diene, triene, diol, triol. You'll notice that these switch to a different prefix. It's not meth, eth, pro, bute. Instead we go di, tri, tetra, penta, and then it does go back to normal. I think I'll just give you this one. But there is a weird thing that happens when you, this is tetrol, 4 alcohols. There is a weird thing that happens when you go from having just a suffix stopper to a suffix with a multiplier. And that's that you put the E back in. So, sorry, if we have CH3OH versus COH4. At least you know that first one? Its full name? You do. Methanol. 1 carbon, alkane, alcohol. Notice that ane gets suffix stoppered by all. As soon as I need to put a multiplier in there, this is a 1 carbon, meth, alkane, ane, because there's no carbon-carbon double bonds or carbon-carbon triple bonds, tetrol. This actually gets the E put back in. So this becomes methane tetrol. And why does the E go back in? I think it's for how it rolls off the tongue. You don't want to say methantetrol. So you put the E back in for that breath, methane tetrol. This compound, methane tetraalcohol, was synthesized and reported for the first time this year. And it seems like a very simple structure. It's just a tetraalcohol on 1 carbon. but it's never been reported before. It's very unstable, hard to make. Very cool. Okay, questions on suffixes? Questions on suffix stoppers? Okay. So methamphetamine, amphetamine is the root. Technically, it's just a common name root. Meth is actually a prefix. So it tells you that there's a compound called amphetamine, and then there's a version where the nitrogen has a methyl group on it. So that's methamphetamine. Yeah. So you could also have an ethamphetamine or propemphetamine, stuff like that. Yeah, I'm sure. I didn't ask. I don't know if you noticed, but
Everyone was thinking it.
uh-huh. The locant tells the location of the functional group on the parent chain. I don't know if you guys have ever heard the word locant before, but I had never heard it before this.
I mean, I see the word loc in there, and I recognize that from locus, which is like a gene site.
Oh, okay.
Yeah.
Yeah, locus and locant.
It's location of the gene.
I feel like they're related, but I don't know the etymological history of the two. So here's the deal. If you have a functional group that is on the first carbon of a 6-carbon chain, you need to say that that functional group is on the first carbon, as opposed to being on the second versus the third. And if it was on the fourth, then that's actually just the third from the other direction. And the fifth is the second from the other direction, and the sixth is the first from the other direction. So we use locants to describe where on the carbon chain these fall. The rule here is that we try to minimize the locant set, and we call it a locant set because sometimes there are more than one locant. By the first point of difference that is to say, if I had one set with locants 2, 5 and another set with locants 1, 6, the first point of difference is at the first locant. 1 is smaller than 2. 1 wins out. But prioritizing the highest priority functional group. And in the case that that highest priority functional group is the same either way you number a chain, then you just go on to the next point of difference. There's some exceptions to this. I want to start with them so that we can see why they're exceptions. This compound has a root cyclohex, a suffix ane, a suffix stopper all. What carbon is the alcohol on? It doesn't matter. It could be on any of the carbons. Doesn't matter where you start. So where are you going to start numbering the carbons? At the carbon where the alcohol is. So you don't need a locant here. This compound is called cyclohexanol. No locant. But now compare these structural isomers. What is the root for both of these structures? Prop. What's the suffix and suffix stopper? Anol. These are both propanol, but they are not the same structure, clearly. So we use the locant to describe their difference. The structure on the left,
Wouldn't your root be 3 for the left one? Or 3 carbons?
pro. 1, 2, 3, pro.
And are you counting the one on the side on that?
Pro. 1, 2, 3. Longest carbon chain.
Oh, okay, right.
Yeah? I don't have to start at the alcohol and move from there.
Yeah, okay.
Similar to, we had that example with the alkene and the ketone, and we would have counted through that longest chain.
Yeah, okay.
So here I can minimize the locant set by numbering from the right to the left. So I get propan 1 all, telling me that my alcohol is on the first carbon of the 3-carbon chain. But to be fair, this is what IUPAC asks for, and many people take that locant and they bring it out front of the whole thing, and they say 1 propanol. There are opportunities for you to do this, and there are times you cannot do it. I'll give you an example where you cannot. This one, propan 2 all, otherwise called 2-propanol. You may know it as rubbing alcohol or isopropyl alcohol. Those names are functional class. They name it as alcohol rather than as a carbon chain. That's what I was doing earlier with the amine. I was making that issue. So locants are one of the most important things in helping us distinguish structural isomers from each other. They tell us where on a carbon chain something is. Now, one of the reasons that it makes sense to put these names, these locants, into the name between the root and the suffix is that if you have truly a suffix and a suffix stopper, or heaven forbid, 2 suffixes, "een" and "ein, and a suffix stopper, it helps you distinguish where along the carbon chain each of those groups actually is. What is our root for the parent chain? No, you see it. What's our root? Bute. And I have a suffix, "-ene," for the carbon-carbon double bond, and a suffix stopper, "all," for the alcohol. So I need to describe where along the carbon chain the alkene is and where along the carbon chain the alcohol is. So I'm going to have these locants that tell me where it is. This is not butenol. This is bute something ene something all. How should I number this molecule? From right to left or from left to right? Better question, which of those functional groups should I prioritize getting its lowest locant? Alcohol, because the alcohol is a higher priority functional group than the alkene. So what would be the best way? Right to left, because I hit the alcohol sooner. So my alkene is at 3, and my alcohol is at 2. This is bute 3-ene 2-all. This is why it's not always good to pull the locants out front. Because if I said 3,2-butanol, you'd be like, what is 3,2 and which one describes where the ene is and which one describes where the all is? However, people do take whatever the first locant is and they pull it out front. which means that the only locant you really have to put in there is the locant for the suffix stopper. All right, what about this one? Sorry. Yeah. You can't do 3,2 butanol. It leaves too much ambiguity. People are going to think that you might have wrote your numbers down wrong, right? And that you meant to put 2,3 butanol. It's just not, it's not clear enough. And for that reason, you can either take one suffix, one locant and pull it out front, or you can take both locants and put them in the middle. Yeah. The whole point of it is to remove ambiguity, to make it as clear as possible. Yeah. What is the root? Cyclohex. Not just hex, but cyclohex. What is the suffix? Will?
Okay, is it diene because there's two double bonds?
Yes. This is not cyclohexene, but cyclohexadiene. Now here's a weird thing. When you have a multiplier, I told you that this A comes back in, even if the suffix is not ane. In this case, the suffix is ene, but this is going to become cyclohexa because it's going to be followed by di before it's followed by ene. So you get this A back in there. And then I need to describe not just one locant, but two locants. I need to describe the two locants of the two alkenes. We're going to revisit alkenes later in the semester. We'll make sure that we understand them well. But just as an intro, when you number an alkene or an alkyne, you have to count through the two carbons of the alkene or the alkyne. So wherever you want to start, you have to number through that alkene. Now, just like here, I didn't need to say cyclohexane 1 all, because of course it's at that one position. But now I do need to put in locants, but I can still start at an alkene position to get the lowest locant set. So if I start here and number through, I only provide the first number of the alkene, 1 and 4. And that's my lowest locant set. If I tried to number counterclockwise instead, I'd still run into 1 and 4. This is cyclohexa 1,4-diene. Natalie, did I confuse you by that?
Yeah, I was a little confused, but now I get it.
I threw you off. You thought I was going to go with what?
I thought it would be 1 and 3.
1, 3?
But now I understand it goes around.
Okay, because I can't start here and then number this way, because then I'm not counting through the alkene. Yeah?
Yeah.
Good.
I have
You bet.
a really weird question. I'm thinking about this. Is the 1,4 necessary? Because no matter which orientation you put these double bonds in, wouldn't it be in the same position every single time?
Good question. No. Structural isomer.
I see what you're saying. Okay, so.
What's the name of this structural isomer, Will?
Never mind. I got it. Yeah. So it's cyclohexa 1,3, right?
Yeah.
Okay, I see what you're saying.
Now here is something you can do. Again, we said that you can pull out these locants in front, but only the locant for whatever the first thing is in the suffix. Here it's just the suffix, right? There's no suffix stopper. So we can call this 1,3 cyclohexadiene. Like up here, we can call this 1,4 cyclohexadiene. technically it goes against IUPAC rules, but it's kind of legal. Make sense?
Yeah.
Isn't it fun? Didn't you want to come to Oakham to learn language?
I mean, that's what it was advertised as.
That's true. Organic chemistry is a second language. And sometimes it sounds like German, right? Like the Ein Ein. It's just got a very German ring to it. Oh, actually, there's a reason for that. I say that like it's random. There were a lot of brilliant German chemists that paved the way for organic chemistry. So I'm sure their language left a mark in Oakham. All right, that's it for locants and suffixes, which means the last part is the prefix. And I actually want to come back at the start of our class on Monday to talk a little bit more about alkane terminology specifically before we go into stereochemistry. So we're not going to finish everything about the prefix today. But I want to remind you that the prefix describes everything not named in the root or the suffix. Halogens get put into the prefix. Little carbon chains that are not a part of the parent get put into the prefix. Other functional groups like the cyano and the ethers, those can get put in the prefix. Alcohols can even be put in the prefix as hydroxy if there's another major functional group that already claims the suffix stopper. So anything that can't be put into the rest of the name gets put into the prefix. So a few things about this. They're alphabetized. It's not numerical. So you will often see locants that are in the prefix that seem totally out of order, and that's because it's the name of the thing that's being alphabetized. Bromo comes before ethyl. Bromo comes after amino, right? A subpoint about alphabetized. It's not alphabetized by multipliers. So if you have dichloro, alphabetized by C for chloro. I'll put that example up here. You're still working to minimize the locant set in the prefix, but you start first by prioritizing alcohols, then alkenes and alkynes, then alkyl groups, just carbon chains, and halogens. So if you have an alcohol, an alkene, or an alkyne, then all of those other groups, they just get whatever's coming to them based on how the alcohol was prioritized. If there is no alcohol, alkene, or alkyne, then you just figure out what locant set minimizes those halogens or those alkyl branches. There are some strange ones. Groups that get put in parentheses. They go by their first letter, whether it is a prefix, or excuse me, a multiplier or anything else. And the reason that something would get put into a parentheses if that group is itself branched. So earlier I gave you guys this, which is one cyclohexyl ethanol. Cyclohexyl is the prefix to ethanol, and it comes off the first carbon of ethanol. But if this group was branched, like so, this is not cyclohexyl, it's now at the first position of ethanol, it is a 2-methyl cyclohexyl ethanol. The substituent of ethanol is cyclohexyl, which has a methyl substituent of its own, coming off of its second position. I can't actually alphabetize this because I didn't put any more prefixes in here, but M is what you would prefix by, simply because it is the first letter inside of those parentheses. Trust me, it will make more sense as we apply it more. The last resource that I want to talk to you guys about before I send you on your way, you have a mandatory bonus assignment. We are using it to assess learning across all sections of OCHEM 1, regardless of instructor or teaching style. You'll find this under the module for Unit 2. It's at the very bottom, and it's due just before your unit test on this, maybe well before, I can't remember, maybe a week before your unit test. It's this alkane nomenclature activity that was not designed by me, but by our course lead. He's the one that chooses the course assessment assignments. So you will find that this does not look like how I draw my structures. It does not look like how I test. It does not necessarily have compounds that I would ever ask you to draw or name. That being said, if you can go through this activity and name these compounds, you will have a very good understanding of everything that we talked about today. So try it, because you cannot lose points. Try parts of it, because even if you don't complete it completely, anything you get right counts towards your bonus points. And like I said, it is mandatory that you submit it. So try it and see how it goes. When we come back in on Monday, I'm going to kind of pick up here from prefixes, because I think I gave some of you a little spook with this methyl cyclohexyl. And we're going to talk about how we come up with those prefix names for carbon chains, which is going to help lead into some terminology about alkane structures. And we're going to use that to segue then into our stereochemistry portion of Section 3 and Section 4. All right? Cool. Have a great weekend, guys. I'll see you on Monday.